Hello everyone. So as I promised, this is the explanation on how you could achieve the bonus points from the transformation coding assignment. Okay, I will not give you the entire solution, obviously, right? Because you need to do it. I will show you a couple of basically hints on how you can solve it and a couple of tricks. Okay, good. So this is an example of what you need to perform in order to get the full marks before the bonus points, right? So basically, this is the solution. There can be two different solutions, right? The main solution and the solution getting the bonus points. So the first is basically using forward kinematics, right? So as we said before, forward kinematics is basically the same as a hierarchy of transformations, right? But let's talk about the actual bonus point solution. Okay, so the bonus point solution needs to be something like this. So it's basically the octopus walking. Okay, so this is way more challenging, right? Because the first one, again, is just forward kinematics. You are just assigning a transformation matrix, in this case rotation matrices, right? And you can use a sine wave to make those arms kind of rotating, and that's perfectly fine. But you don't have control of the actual endpoint from those arms, right? The end effector, as we call it in inverse kinematics. This is different, right? Because in this case, if the octopus needs to walk, you need to define the actual position of the end effector of your kinematic chain. So you need to solve this problem as an inverse kinematic and not as forward kinematics. Okay? Okay, so what we have here is a very similar scene to the one that you saw with the actual solution. So if I play the animation, right, as we can see, basically the octopus is walking, right? It means that their legs, right, the tip of their legs is basically following a certain pattern, okay? So let's see how we can achieve that. So as you can see, the body of this octopus, it also has a certain animation, right? Which in that case will be just a transformation matrix using sine waves, for example, right? But I will get rid of that animation for now, just temporarily. So I will get all the keyframes from this head, and basically now the head it doesn't have any animation at all, right? And I will basically hide all the legs, and I will only show you one single leg, okay? So if we see this arm from a front view, right, we can see that this is just this is a solution for an inverse kinematic problem, right? So what we have here is that the tip of this arm is just following a certain path, right, from an end effector, right? So remember, the end effector is basically the end position of the tip of your entire kinematic chain. So this pink line here is basically representing the actual path that the end effector is following, right? So this is actually the path, right? So as I said, it's basically following a straight line at constant speed, and then at constant speed is basically just following this this curve right here. So what type of curve is this one? Well, it turns out that is a quadratic Bezier curve. So combining a quadratic Bezier curve that gives you a parabola, and with basically a straight line in which you will move your end effector in a straight line at constant speed, you get this effect, the effect of a walking motion, right? And the trick also is on the floor, because if I show you the floor, you will see that basically what is happening here is that the floor is moving exactly at the same speed exactly at the same speed as your end effector is moving at this straight line, right? So because you're basically at the end you're controlling everything, but in your code, if you're moving the end effector in a straight line at a constant speed, you know that speed, right? So you can use exactly the same speed to modify the actual position of the texture in your plane to basically mimic that motion, right? So this is, in the end, what is happening with one single leg. So now, if I show you all the legs again, you will see that basically all legs are doing exactly the same. They're just following, right? So it's kinematic chain is just following, right? A specific is following an end effector, and those end effector, which is just a position space, is basically following a certain path. In this case, it's just a straight line combined with a Bezier curve. So the only difference between those between each leg is that they're just moving at different time, right? So they're just starting its animation at different speed. Not different speed, sorry. They're all moving at the same speed, but they're just start their animations in a different time. So it's just an offset, right? So as you can see, for example, in this first two legs here, you can see that the leg that is behind is just started the animation before, right? They're moving exactly at the same speed, and they're moving exactly in the same path. So the only thing that we need to add is basically a movement for the body, right? So what is happening there? So it turns out that there is the origin of your kinematic chain, in this case, is this sphere right here, right? These spheres, right, which in this case are basically, again, the origin of each kinematic chain, right? They're basically attached, or their parent is basically the octopus body, right? So that way, if now the body is also moving, if you create a different animation for the body, and you can use, for example, sine waves to define a certain rotation, right? So you get the end result, right? This weird creature basically walking. So this is what conceptually is. This is what is happening here, conceptually speaking, right? It's just this an inverse kinematic problem for each leg, and the trick is that we are just making the end effector for each inverse kinematic problem to follow this exactly the same path. That is a combination of a straight line at constant speed and a quadratic Bezier curve, and they are all following exactly the same path, but just with a specific a different offset in time. So now the question is, how can we actually solve the inverse kinematic problem? Okay, so this is basically my kinematic chain, right, with two links, only two links. This right here is my kinematic chain, which means that this is basically the origin of my kinematic chain, and this tip is basically the object that I need to touch the end effector, right? So basically, by giving the end effector position, I need to get this the entire transformation matrix, the entire transformation information, to get these objects to basically rotate towards touching that position, right? So I will create an object to represent that point space, right? So it will be a helper, it will be a point, and it will have a certain size, and I will put it, for now, let me just put it right here, right? Okay, and I also will get this guy to 0, 0, 0. You will see that in the end is not a problem if it's not, but for now I just want to kind of constrain the problem. For now, it's just in 2D, right, to see what is happening here, right? Okay, so this is the origin of my inverse kinematic problem, and this is the end effector, right? So I will call this end effector. Okay, good. So I will just create variables at the beginning. So I will say that variable L1 is equal to the object L1. Good. So now I have my variables, right? I need to compute the actual intersection between those circles, right? So I will create another object that will basically represent that intersection, right? So I will create just a sphere, quickly a sphere. I will call this intersection, right? And I will also create a variable here. Okay, so now I will create a function to actually compute the circle-circle intersection, okay? And so I will create this function right here. It will get, let's say that is, the name is circle-circle intersection, and it needs to get basically it will basically need to get the center of these circles and also the radius of the circles. But in the end, all the information is already contained in the objects L1 and L2, right? So I will just say that it needs to get L1 and L2, and it needs to get also the end effector, right? Because I have, yes. So I need the radius for both circles, and also I need the origin for both circles. So the origin of one of the circles is basically the origin of the first length, but the origin of the second circle is basically the end effector, right? So I also need the end effector, right? And again, we can just use different names, but for now let's use this thing, okay? So I will use that, and let's see how we can actually compute the intersection using this theorem, right? So again, the theorem says that, so let's just make a very quick recap. Okay, so let's see this image here, right? So this is basically exactly the same theorem, right? Or exactly the same geometrical construction, but just with different options or different sizes or different type of triangle. So basically, we have 4 distances. We have A, B, C, and D, right? And the theorem says that A over B is equal to C over D, right? So what do we have right now? So we have the origin of the kinematic chain. We have L1, which is basically the first radius. We have L2, right? And we have this position, which is the end effector. It means that we do have A, right? So we first need to compute, the distance C, and we need to compute the distance B, okay? So distance C is basically the midpoint between S2 and S1. And S1 is basically the intersection between this circle, the radius of the circle, with this vector right here, which is just basically just this distance, okay? So what I will first compute is basically the distance between the origin to S2, and you will see why, okay? So I will just compute that distance, right? This distance right here. So what is this distance? That is basically the vector A, this entire distance minus this radius, or the length of this link, right? You agree? So basically A minus L2 will give me this distance right here, right? Okay, so I will say, I will call it, just to use the same names that I have in the theorem, right? So I will say this is equal to distance A. Oh, by the way, I don't have A yet, right? So I need to compute a vector, right? So I need to compute vector A, yeah, is equal to basically the position of the end effector, right, minus the origin, right? So it will basically end effector dot pos minus the origin of the kinematic chain, which is in this case L1 dot pos, right? So L1 dot pos is this one. This is the end effector. So basically I'm subtracting this position minus this position. I'm getting this vector right here. So I can compute the variable A as the length of vector A. And that's it. So now I can say that this variable right here will be basically A minus the second radius. And the second radius is basically the height of this object right here, which is basically representing the second radius, right? Okay, so we first compute that. Okay, so once we have that, we can now compute the distance c, right? So distance c will be equal to L1 minus this O, the distance between the origin and S2, right? Let's see why. So let's see why that is distance c. So if we open this again, right, this distance c is basically L1, which is basically this distance from the origin to S1. This is exactly the same because remember S1 is the intersection between the first circle with this vector here, right? It's basically this distance minus the distance between the origin and S2, right? Good. So now that we have A, we have C, we need to compute B, right? So now we need to compute B, and B will be equal, it will be equal to the distance between O and S2 plus half of C, right? Because basically, yeah, remember that we are computing with point M, and M is basically the midpoint between S1 and S2. So it will be half of this. So we have B, good. So we have A, B, and C. The distance that we don't know is distance D, right? But the theorem says that A over B is equal to C over D, right? So if we just do our algebra, we'll see that distance D is basically equal to B times C over A. And that's it. Yeah, that should work. Okay, good. So now I have that distance, right? Now that I have distance D, right? And I need to basically compute this position right here. It means that I need to get the normalized vector OP, right? So basically this direction. And I need to multiply that direction times this distance between the origin and S2 plus distance D, right? Good. So let's see. So point J will be equal to, so J will be basically vector A normalized times distance from O to S2 plus D, right? And we will need to add the origin of the kinematic chain within this case, which in this case is L1, right? So we can check that, and we can, this is not yet the actual circle-circle intersection. This is just the point J, like lowercase j, right? Which is basically the projection of the intersection into this vector, right? And but I can test, right? So I can basically do this. So this object right here, the intersection dot pos, will be equal to the circle-circle intersection with L1, L2, and then the vector. Yeah. So let's check, and this is basically the position, which actually kind of makes sense, right? So now let's try to actually compute this circle-circle intersection, right? So that is the point J, and now we need to compute the this distance right here, right? So we can use Pythagoras for that, and but the problem is that with Pythagoras we can compute its length, and it's very easy, right? Because we have this distance right here, and we have this distance right here, right? So we can compute this distance, right? But we need to get that direction. So in order to get that direction, we need to define it, that direction. So we can define the direction using cross product. So what I would do is, I have the vector that is coming from O to P, right? And I can define an up vector. So this is similar to what we did with the camera transformation. So I will define an up vector, right? Which in this case, I will just use a unitary z-axis, right? So if I take that unitary axis, or imagine that I have a unitary axis here, right? Unitary z-axis, and I take the cross product between this vector here and that vector there, I basically get a vector that is orthogonal to this plane, right? So it's basically a vector that is coming out from my computer, right? Then if I already have a vector that is basically orthogonal to the plane in which we are solving the inverse kinematic system, and this is super important because the thing is, we are solving the inverse kinematic problem as intersection between two circles, and the intersection between two circles basically describes a triangle, and a triangle is basically always on a plane, or a triangle represents a plane. So what I'm getting by taking the cross product between this vector times a unitary z-axis vector is basically a vector that is orthogonal to this plane, to the plane in which I am solving this problem. So once I have that, I can now take another cross product between this vector and that orthogonal vector, and I will get a vector that is orthogonal to those vectors, which will be exactly this one. Okay, do you agree? I guess you do. I guess you do. Okay, so I will let's call that we can actually send that into the function, the op vector, for example, because this is interesting. The op vector will basically define the actual orientation of the plane in which we are solving the inverse kinematic system, right? So that is very important. So I will actually send it on my function. So I will call it op vector, and I will send it at the end. So I will say it's 0, 0, 1, right? So I need to get, I will call axis. So I will call it plane normal, right? Because again, I'm solving the inverse kinematic problem as a triangle, and a triangle represents a plane, right? So this vector that I will compute is basically the normal of that plane. So I will call it like that. I will call it plane normal. And basically plane normal it will be equal to the cross product between the vector A and the up vector, right? And here the order is important, right? So in this case, let me think about it. Yes, this is correct. So basically, if I am taking the vector A cross up vector, I am using the right hand rule, and I will get a vector that is orthogonal to that plane and is on my right. It's basically pointing as my right thumb, right? So that will be the plane normal. Yes, good. Okay, so now I need to get the actual, this vector right here, right? So I'm already have a vector that is pointing out from my monitor, and it's basically orthogonal to this plane. And now I need to compute this vector, right? So this vector, again, using the right hand approach, right, needs to be the normal cross the vector A. Yes, normal cross vector A. So let's call it, I don't know, I will call it J vector. So J vector will be equal to vector, and again, you're not seeing me, but I'm just moving my right hand kind of like trying to understand what is the actual order that I need. So I need to get, yeah, so it will be plane normal with vector A. Yes, so basically the cross of that, right? However, we need this guy to be normalized, right? Because we will basically multiply this guy by, yes, we need to multiply this guy by some distance, right? So now I can say that the actual intersection, yes, so the actual intersection, circles intersection will be equal to J vector, right? Yes, J vector times, oh, I haven't computed that distance, right? I haven't computed this distance right here. So we need to compute that distance. So let's call it opposite leg, right? Because I mean, if we use it, the Pythagoras theorem, that will be basically the opposite leg. Yeah, so opposite leg is equal, the opposite leg is equal to, yes, okay, so the opposite leg will be basically the square root of this guy here, which is basically the leg 1. Sorry, yeah, so this basically, it will be this, the square of this minus the square of this distance, right? So the square of this, minus the square of this distance, which is basically O to S2 plus T. Yes, okay, so now, yeah, so opposite leg is basically that distance already. So the circle intersection will be basically the J vector times this. Okay, and so yeah, so it's J vector times the opposite leg, but we also need to add J, right? And oh, I have a mistake here. So yeah, remember the theorem is, yeah, so this needs to be B times C over A, right? Yeah, so I had a typo there. Okay, so this should be the actual intersection, right? So, well, it means that this position right here was actually incorrect. So this should be the actual intersection. So if I run, well, I haven't run it, obviously. Why did I erase this thing? Oh yeah, what I'm sorry, I don't know when I don't know when I erased this line of code. Whatever. So yeah, so I can just run it again. And yeah, so this should be the intersection, right? So let's see if I am correct, if it's true. So what I can do right now is just for visualization purposes and for debugging, this is a great thing of coding here in 3 to the max. That, I mean, everything is just visual, and it's the perfect way of debugging graphics things. Okay, so I will create a circle with a radius 20. And I will create basically two circles. So the first circle will have so we'll have a constraint. It will have a position constraint to this object right here, which is basically the origin of our kinematic chain. And this guy will have a position constraint with this guy right here, right? And yeah, it seems that the intersection is actually correct. So actually, I will just animate this thing because it's obviously more interesting, right? So I can get the end effector, for example, and I can just do a animation. So I will just I don't know, move this guy here, and then I don't know, maybe here, and then go down a little bit, and I don't know, maybe returning to the same position at the end. So I have an animation, right? And I need to now, I mean, compute this not a single time, but several times, one per each frame, right? So I need to say animate on for t from 0 to 100, do the following at time t. This is just a recipe in 3 to the max to basically compute everything for each frame and just animate stuff, right? So I compute everything, and I play, and there you go. That's the intersection between those circles, and it's perfectly fine, and it's very simple. Okay, good. So now what we can do is actually compute the transformation matrix with this information that we have already. Compute the transformation matrix for these guys right here, right? That is in the end our goal, right? Good. So let me just save this guy. Okay. So we have the intersection already, right? So for each frame we have the intersection. So now we need to compute the transformation matrix. So what we could do is Okay, so 3 to the max has a function. Yes, so it has affine matrices also, right? 4 by 4. The thing is, 3 to the max, if I remember correctly, uses row notation instead of column notation. I think so. Yes, I think. Okay, so I will do basically another function. I will call it lookat transformation. There's actually a very easy way to do this in 3 to the max. That is basically just calling. There's a property on objects that is called .dir. That's basically the vertical direction. So if I just said .dir equals, I mean like link .dir equals to this vector right here, which is basically like the position from the intersection from its origin, it will be very easy. But that doesn't exist on JavaScript, right? So yeah, I want to give you all the tips and basically everything. Okay, so I will use so let me think about it. What do I need here? So I need to code. Okay, so we will send 2 positions, right? The position of the object and the position of the target. So we can say something like obj pos and target pos, right? And we need to send also an up vector, right? Up vector. Yes. Okay. So this is a function. Oh, sorry. And I need to like this. And this is a function. So this function, I need to create first a matrix, a 4 by 4 matrix. And the way is in 3 to the max. I will call it new matrix, whatever. I think it's matrix 3. I mean, it's a weird name because it's actually an affine 4 by 4 matrix, but the class is called matrix 3. And I will put 1. It means that it will create a identity 4 by 4 matrix. Okay, so I will compute the lookup vector first, right? So the lookup vector is equal to the target position, right? Pos minus the obj pos, and what we need to normalize this guy, right? Right. Yeah. Okay. So the lookup vector is this guy normalized, and then we need to say that the new matrix, the first row of the new matrix, row 1 needs to be basically the cross product between the lookup vector and the up vector. Yes. Okay, new matrix. And again, this is row 1, row 2 because they use row notation, right? So remember, row 1 is basically like column 1 for our column notation. So, but it's basically the Z direction, right? So next, this one will be cross the first row, right? Cross the Z axis, which is already there. So it's new matrix dot row 1, and you're probably hearing my daughter. Okay, row 1 and lookup vector, right? And the new matrix dot row 2, no, row 3, sorry, will be the lookup vector, because yeah. Yes. So remember, the lookup vector is basically the z-axis, right? So the z-axis is the lookup vector, which is the third column, or in this case, the third row. So the first row is basically taking the lookup vector, cross the up vector that give us the right vector, which is the x vector, right? It's exactly the same as we did, or it's almost the same as we did with the camera. And then to compute the actual y vector is by taking the cross product now between that right vector and the lookup vector, and the lookup vector is basically the z-axis, right? Yeah. The only difference again is that the camera, remember, the z-axis from the camera is basically pointing to the opposite side of the lookup vector, and I'm not doing that right now because I don't need it, right? So yes, so now we can just return the new matrix, and then this guy is L1. So then on the animation, give me a second. We need object position, target position. Now, but we need to also, we need to modify. We need to also add the translation, right? Yes. So we need to add the translation. So we need to add the fourth row. So new matrix dot row 4 will be equal to, in this case, is the object position. Yes, in this case is the object position. And depending of which link we are using, you will see that we will change that, right? Obviously. Okay, so yeah, I think that's correct. So basically these first rows are the rotation part of our 4x4 matrix. This is our x, y, and z basis vectors, right? And this is just the translation, right? Okay, so now we can say L1 dot transform. So dot transform from an object in 3D is basically the entire affine matrix that is defining its transformation with the with the world coordinates. So this is something interesting. The way I will compute the entire system is not by making a hierarchy, right? So I don't even have a hierarchy. So for example, right here, if I move this link, this link is not moving with this one, right? So, and the way I'm computing everything is because I'm just computing the position here. I am creating the entire transformation matrix in world coordinates for each link. So there will not be actually actually related as a parent, one from each other, one from the other, but yeah, I mean, the relation is just because they will basically share that point of intersection, but they will not be child and parent. Yeah, I'm defining their transformation matrix with respect to the world coordinates using these two positions. So I will say L1 transform is equal to this function right here. And so now what do I need to send? So the object position in this case is basically its own position, because we are using its position as the origin of our system, right? So the target position will be the end effector dot pos, right? And the up vector will be the same. This will be the end effector, and we compute it. And no, sorry, this is wrong. The end effector, sorry, the final or the target position is not the end effector in this case. It's the intersection, right? It's intersection position. Yes. Okay, good. So now if I play the animation, now this guy is correct. It's correctly placed, right? The only weird thing that is happening is that somehow it's scaling. It is scaling. Yeah, I think, let me think what is happening. Look at vector normalized target.pos. New matrix row. This is usually happens because because the vectors are not normalized. Oh yes, this is the problem. the look, oh, no, it's normalized. What is happening here? This shouldn't happen. Okay, I will fix that later, because right now I'm just want to check if what happens if I get the other object, right? And we can check that later. Okay, so L2 transform will be the same thing. Look at transformation. Now its origin is not L1.pos, right? Its origin for this guy, the origin will be this guy here, right? So it will be intersection.pos, the first position, and the end position will be the one from the end effector, right? And the same of vector. Yes, okay. So yeah. So now we have an inverse kinematic solution, right? But still, I have this problem, right? I mean, it seems that it's scaling. So let me think what is happening here. Okay, so what apparently is happening is that the resulting vector from the cross product operation is not unitary, is not normalized, which is weird, because I guess this is just a bug, because I had to normalize the results. They should be already normalized, because see, look at this. The lookup vector is already unitary, right? Because I'm normalizing this guy. So the lookup vector is unitary, right? This guy is unitary. And the up vector is also unitary, because this is the guy I'm sending, right? So these are two unitary vectors. And so the cross product should be unitary, right? However, it's not. I don't know why. So yeah, and again, I will not fight right now, because I should keep this tutorial as fast as possible. So I just normalize everything, and that's fine. And now we don't have any scaling, and this is our beautiful inverse kinematic, right? And the beauty of this is that apparently we are solving everything in 2D. And not apparently, we are actually solving everything in 2D, because again, we are solving this system as a circle-circle intersection, which basically represents a triangle, and a triangle is always representing a plane, and so it's 2D. But the thing is, it will also work in 3D, so you will see what happens. The thing is, what we are doing right now is we are sending an up vector, right? And by taking this cross product here, in which we are defining this plane normal, right? It doesn't matter if we move now everything out of the front plane, the solution will still be on a plane, right? But now basically the plane will move. Okay, so let me show you something, and you will see it's very cool. So I will put, for example, okay, first thing that I will do is just reduce the size of these guys, because they're just too big. They look weird, honestly, they look weird. Okay, so I will do something like this, and I will also reduce the size of this thing, and I will, for example, create a helix. I just want to experiment, and I want you to see that we are actually solving also in 3D, and that we actually don't need to change absolutely anything. So I am creating okay, so this end effector here, and I will, I don't know, increase the turns of this guy. Yeah, let's do something like this. It's just a spiral, right? So I will get this guy, and I will go to animation, path constraint, and I'm telling this guy basically that he needs to follow this path, right? I mean, this animation is already not valid anymore, right? Because I mean, I'm not erasing the animation, so I can take all these objects and basically erasing these frames, and I will for now just hide these circles because we don't need it, right? Object properties, sorry, hide selection. It's not working. Hide selection. Okay, good. So now the end effector is basically moving now in 3D, right? So it's not constrained to this front plane. So if I come back to my editor and I just compute it again, let's see what happened. And it is following everything in 3D. So it's super nice, right? It's nice. And what happens if we get this guy, right? And let's see. Let's remove the animation, right? And I will animate the position of this guy, right? So I will basically, I don't know, maybe move this guy up and then a bit in this direction, right? So I compute it again. Yeah, and it's still working. See? It's totally in 3D. So the solution lies on in a plane, right? But now everything works in 3D. It's perfectly fine, right? We are solving as a circle-circle intersection, which is very convenient in terms of coding, and it works perfectly fine. And the origin can also be moved, right? So in this case, the origin, remember, is it needs to be just attached to the body, right? It needs to its transformation metric needs to be multiplied by the transformation of the body, and that's it, and that's perfectly fine, right? Good. So now is okay, Enrique, but the thing is, this is still the solution for only 2 links, right? So how can we compute the solution for several links, right? So let me show you how you can do it. And I'm already giving you basically the entire code, right? You already saw all the math that you need for actually solving the inverse kinematic problem for 2 links in 3D, right? You already have that. So I will show you the hint and kind of like the theoretical explanation of how you can actually achieve it for multiple links. But it's very, very easy, okay? Okay, so I already show you this example on the other lecture, but I think it will be easier for you now to understand, not that you already saw the math involved, right? So what is happening here? This kinematic chain, or this inverse kinematic problem, is also using this exactly the same paradigm of an inverse kinematic problem with 2 links. The only difference is that the first link has a variable length, right? So what does that mean? So we know that in order to compute the circle-circle intersection, we need the 2 links, right? We need the radius of these 2 circles. So the first link, which is this one here, is used in here, right? So basically when we compute C, we use the height of the first link, or the length of the first link, or the radius of the first circle, which is this guy right here. And right now, this variable here is basically fixed, right? This variable is fixed. And also this one, right? I mean, when we were computing the previous example, the radius of those circles, or the length of those links, were basically fixed. We were not changing that to any, right? So the trick is that now this will be a variable that can change over time, and it will change depending on the distance or on the distance a. So let's see. Let's analyze this guy here. So please pay attention to this thing. So this link, imagine that this link, it has 2 pieces, right? But imagine that it's a single link, okay? It has 2 pieces, but it's a single link. So this position here, or this object here, represents the minimal distance from this link, okay? It makes sense, right? If I take, I don't know, if I could take everything and I could move it inside this space here. Sorry, I'm missing this guy here. Oh, sorry, it has a path. I cannot move this guy, but whatever. So the thing is, imagine that if I collapse this thing here, this like telescope mechanism, right? It means that this distance is basically the minimum distance that this guy can have, right? So the first link has two distances, a minimal distance and a maximum distance. So the maximum distance will be this one, right? When it's basically like fully extended, right? So this link, again, has variable length, which basically it means that it has two possible distances, right? A minimal distance and a maximum distance. Those two distances right now will be defined by the user. Okay, so imagine that you define those distances. I mean, I define those distances by modeling this guy right here, right? So you can say, okay, the minimal distance will be whatever, 20, and the maximal distance will be 40, okay? So the question is, how can you decide which distance are you using, right? So which final distance are you using, right? If it's the minimum, the maximum, or something in between. Well, that will depend on whatever function you want to use, but it could be, for example, a linear relation with respect to the distance between the origin and the end effector. Makes sense, right? So imagine that the end effector, right, is very far, like in this case. If it's very, very far, actually in this position, for example, is even farther than the actual sum of the distance between, sorry, the length of the link 2 and the maximum length of link 1, right? So if that distance is, if the distance from the origin to the goal is actually like larger than that, right? It means that this guy needs to be at its maximum extension, right? But if it's closer, right, it means that it doesn't need to be at maximum extension, right? So what you do is basically you can have like just a linear function that basically modifies the actual length of this link depending on the distance between the end effector and the origin, right? So that is how you can basically compute the inverse kinematic problem as this example right here, right? With a variable, with a link with variable length, okay? And how that is related with having several links. So give me a second and I will show you another example. Okay, so now let's see this example. Okay, so this is an inverse kinematic solution, right, which has a kinematic change that it doesn't have two links anymore, right? It has three links and it's working perfectly fine, right? So the trick here is that what we are doing here is we have three links, right? But we are first solving the inverse kinematic problem as a two-link problem. So let me show you something. There's something hidden there, right? There's something hidden here. So first we solve with using this end effector and this origin. We first solve the problem with a virtual or fictitious variable length link that is here, right? And what happens is that with that variable link, which basically has its minimum size, will basically or can basically this distance, right? So basically the distance of the first link, and the maximum height or the maximum length will be basically the sum of these links, right? And again, you define its dynamic length as a linear function with respect to the distance between the origin and the end effector. I mean, it can be linear or it can be whatever you want. You can also play with that. You can play with on how you control this variable distance, right? But basically having a dynamic distance for that fictitious link, you end up with this position, right? Well, this position now, it's the end effector for this system, right? So basically, what you do with a lot of links, right? When you need to solve this with a lot of links, you basically solve this problem recursively from the end effector to the origin, right? Using variable length links. That is basically the solution, right? So basically, what we can see here with only an example with four links is basically this this thing right here, right? So if I have in this case, for example, 4 links, right? L1, L2, L3, and L4. I first solve with the first 2 legs, right? Which is basically this. I'm solving for L1 and this virtual link right here. And this virtual link right here, or this fictitious links, will have a variable length, right? Which is dynamic in respect to the origin to the position. So the way I compute this point J1 using the theorem, then I compute this point right here. So now I have the origin for the L1, L4, and I have all the information, all the necessary information to compute basically the transformation matrix from J1 to, for L4. And now this guy will be the end effector for this next system of 2 links. And now this solution of that system will be the end effector for the next system, right? So basically, you just solve it recursively, like backwards, right? And that's it. That is exactly how you can go from this super easy and yeah, at least in my opinion, it's very straightforward math, and it's just a couple of lines of code from this like 2-link solution. You basically go from there to the octopus, to the octopus walking, right? Is basically that, right? So as you can see, each leg of the octopus has basically 3 links and is solved exactly as I told you, right? It's just a inverse kinematic problem with an origin that is animated, right? Each origin of the legs is basically animated because it's basically inherit its position from the animation from the body, right? And the tip of each arm is just an inverse kinematic problem solution. It's just an effector that is basically moving along a path that is a combination between a straight line at constant speed and a Bezier curve, right? And that's it. It is challenging because you need to implement this in JavaScript, so it will be challenging. There are maybe just a couple of details that maybe I'm not totally computing here, right? Because this thing of several links, I want you to like solve the problem by yourself. But I gave you all the details already. And yeah, that's it. So good luck, and I hope you can enjoy this.